All right, we had two problems we didn't quite get to, so let's go ahead and just take care of it. Because after all, we want to get all the problems solved. That's one great way to do the test, by the way. Solve all the problems. Remember that. Pro tip. So the first one, find the solution for x double prime minus 6x prime plus 13x equals f of t, and we're given initial conditions at x of 0 and x prime of 0 both 0. These are wonderful initial conditions, our favorite kind. Now you might be thinking, wait a second, we can't solve this for x because we don't know what f is. Now, normally, that would certainly pose an obstacle. So what do we mean by solving for x? Well, what that means is we want x equals something with no x's involved. So it's okay if our expression involves some arbitrary f of t. The goal is, again, x equals stuff without x. So that's what we mean by a solution. And it is possible using what we've learned. Okay, so where do we start? Well, you might say, hey, we've been learning about Laplace transforms, so let's start with taking a Laplace transform. Great idea! You got it! All right. So we're going to take the Laplace transform of both sides. And we can use linearity. So we can say the Laplace transform of x double prime minus 6 Laplace transform of x prime plus 13 Laplace transform of x is equal to the Laplace transform of little f. Okay, with our initial conditions of 0 for x and 0 for x prime, that tells us that these transforms are actually super easy. So we get s squared capital X minus 6s capital X plus 13 capital X equals, and over here, capital F. Well, okay, so this is s squared minus 6s plus 13 capital X equals capital F. And now we say, aha, here's the answer. Capital X is equal to F over s squared minus 6s plus 13. Okay, now, are we done? No. Why? Well, this is a capital X. So in other words, we've now solved for the Laplace transform. We want to get to just little x. So we somehow have to take the inverse Laplace transform. And there's challenges because we have no idea what f is. But, why let details stand in the way? What are some things we can do? Well, one thing is, let's clean up that denominator. Does it factor? I don't really see a good way to factor. Does it have a nice complete the square? Let's find out. So this would be capital F upstairs still. And then we have s squared minus 6s. And then we ask the question, what do we need? What would complete us? Well, you take that minus 6, divide by 2, gives us minus 3, and then you square that. That's a plus 9. So, well, I'm supposed to get to 13, so we'll add 4 more. So we say, okay, so that's really f over s minus 3 squared plus 4. All right, great. But still, how do we take the inverse Laplace? Now, normally we'd be stuck, but we can use the tools we just learned and say, all right, we have two things that we want to take the inverse Laplace of. We have this f, and we know how to take the inverse Laplace of f because it's little f. And then we have this other part, s minus 3 squared plus 4 downstairs. And we actually know how to take the inverse Laplace of that, right? So in other words, think of this as a product of two things, namely as f times 1 over s minus 3 squared plus 4. And so we have our capital F, and we're thinking this as capital G. So we're saying, it's a product. And now we say, hey, isn't there a rule that tells us how to go from a product and take the inverse Laplace? Well, let's grab our chart. I happen to have one with me because, of course, you should always keep one nearby. You know, you never know when you're traveling when it might come in handy. And, this one doesn't have the rule I need. Okay, so we're just going to remember the rule. All right, so what's the rule? So the rule says, we'll recall it, that if we take the Laplace transform of f star g, that's equal to Laplace transform of f, Laplace transform of g, which is fg. Another way to say this is that the inverse Laplace transform of fg is equal to f star g. All right? So we're able to go backwards. Every rule about Laplace transforms has a corresponding rule for inverse Laplace transforms. So it's good to say, I can state both of them. I know how to jump back and forth. Okay, well, we're almost there. What do we need? Well, we're fine with this f. We know how to do that. Now, this last piece, we should clean it up just a smidge because it's not quite exactly of the right form, but it's really close. What do we need to do? Well, okay, so we're going to keep our f as is. And the thing is, this 4 downstairs is really a 2 squared. And we'll need to have a 2 upstairs instead of a 1. So we put a 2 upstairs. And then, of course, put a half in front. So we know the inverse Laplace of capital F is little f. And here, the inverse Laplace of this piece will be 1/2 e to the 3t sine of 2t. All right, so we're almost done. We're rounding the corner. We now can say the following. So x is equal to, well, we're taking the inverse Laplace here, so it's going to be our f convolution, that's what the star stands for, 1/2 e to the 3t sine of 2t. Well, okay, and then, just for good measure, how does convolution work? Well, so this is the integral, 0 up to t, of the first function, f tau. Then the second function, where it's, instead of t, it's t minus tau. And there we go. That's what we wanted, right? We wanted a solution, which means we wanted to say, we wanted to get x by itself. So that's what a solution means, get x by itself. And we have. So in this case, we say, look, x is this expression. There's no x involved. There is f, but that's okay. We should expect there to be an f involved. And we're done. What? All right. So this is an example of how we can use convolution to solve things. And it's just that our answer will involve our function, unknown function, on the right-hand side. Beautiful, beautiful. Use Laplace transforms to find a non-zero solution to tx double prime plus t minus 2x prime plus x equals 0 with x of 0 equals 0. Now we should note that, of course, a zero solution is the function x of t equals 0, which definitely satisfies that expression. Okay, so we have to do a non-zero solution. And we might say, well, gosh, how do we start? Well, the problem tells us how to start. It says, use Laplace transforms. Great, let's start there. Okay, so let's write down a few things just for reference so we can have them there. We're going to need, we're really going to need sort of 3 rules to remember. So the first rule is, what does the Laplace transform of just x double prime look like? Well, that's s squared capital X, then minus s x of 0 minus x prime of 0. Now, the good news is x of 0 equals 0. Great. What is x prime of 0? We don't know. Oh no, did they forget to tell us? Or is something else going to happen? Stay tuned to find out. Okay, we'll also need to know the Laplace transform of x prime. And, well, that's very similar. It's s times x minus x of 0. The third thing we're going to need, and we'll write this down for reference, is what happens if we have the Laplace transform of t f of t. Well, that's minus f prime of s. Okay, so those are our three rules. So we grab those three rules from our list, and we're ready to start. All right, so to begin, well, we say, okay, let's start with this expression. We're going to rewrite it slightly before we take our Laplace transform. So it's tx double prime plus tx prime minus 2x prime plus x equals 0. Now you might say, you distributed. And then you might say, wait, why? Well, the reason we distributed is we can handle tx prime, no problem. We can handle 2x prime, no problem. But we don't really have a good way to handle t minus 2 times x prime. And so, in essence, we actually don't have a really good way to handle multiplication, right? There's no Laplace of f times g works out nicely. Now we have f star g works out nicely. But f times g, kind of hopeless, except for a few special cases, which are t's, because we have this nice rule, and exponents, because we have a nice rule, and, unit step functions, because we're going to get a nice rule. But generally speaking, multiplication is bad unless we're one of those three things: exponents, exponential functions, powers of t, and unit step functions. All right, so here we go. So we're going to go through this a little slowly to start, and then we'll make sure we don't get lost in the details. So we are going to take the Laplace transform of everything, so we'll just start with that. So Laplace transform tx double prime plus Laplace transform tx prime minus 2 Laplace transform of x prime plus the Laplace transform of x equals 0. The Laplace transform of 0 is 0. Now, some of these things are pretty quick. So, for instance, the Laplace transform of x is capital X, no problem. Laplace transform of x prime. Well, remember, x of 0 equals 0. So, in fact, these terms go away. And so this term is going to be s times x. Now, those are the low-hanging fruit. Let's tackle this one. tx prime. How do we handle that? Well, we have this rule that says, if I have t something, then I take minus the derivative of what that would have been. So this part right here is going to become minus the derivative, I'm going to just emphasize derivative with respect to s, of what would have happened if we just took the Laplace transform of x prime. Well, we know that. That would be sx. What about this part? Well, same idea. So I have t something, right? So it's going to be minus the derivative of what would happen if we just did that something. So this is minus the derivative of up here. Well, that's s squared x, and then minus x prime of 0. All right, so there we go. That's what's going to happen. Now, remember, we don't know what x prime of 0 is, but do you notice what's going to happen next? It's really cool. It's going to disappear. And why will it disappear? Well, because we see it's a derivative of a constant. So, hey, life is good. Life is wonderful. So, all right. So what do we get? Okay, so updating here. That's going to go away. So we'll have, will it fit here? All right, let's move it over here for right now. So don't forget the minus sign. When we take the derivative, okay, again, that goes away. Product rule, because capital X is a function of S. So the derivative of the first times the second plus the first times the derivative of the second, capital X prime. Minus, again, product rule. Derivative of the first, 1, times the second, plus the first, times the derivative of the second. And then minus 2s capital X plus capital X equals 0. Okay, well, if everything works out nicely, things should happen now. Well, does anything nice happen? Well, we have here a minus x, there a plus x. Okay, so those cancel out. That's good. Now, unfortunately, these minus 2x's don't cancel. They combine. Their powers combine. Well, that's all right. That's okay. So we have, well, let's just work this all out. So we have, for x prime, we'll have a minus s squared and a minus s, and that's multiplied by x prime. And then we have a minus 2s and a minus 2x, and so that becomes a minus 4sx and equals 0. All right, good. Well, what can we do? What can we do? Well, we're actually kind of in luck, right? Because what's going to happen, everything that's left has an s. Okay, let's just divide out. So this is minus s plus 1 x prime and minus 4x equals 0. Okay, so, well, now rearrange things. We get x prime times s plus 1 equals minus 4x, or x prime over x is equal to minus 4 over s plus 1. Okay, cool. Now we're like, a differential equation inside the Laplace transform. Yeah. Cool. Well, okay, what do we do? Well, we solve this. Now, we actually kind of are on the track, right? We're in our separable mindset. So we've actually just separated, so if you integrate both sides, this tells us that natural log of x is equal to minus 4 natural log of s plus 1. Well, of course, that's the same as natural log of s plus 1 to the negative 4. So that x is equal to 1 over, because that's what the minus exponent means, s plus 1 to the 4th power. All right, well, we're almost there, right? We're almost there. So, where do we finish up? Well, we now know the Laplace transform of x, right? We figured it out. We said, hey, the Laplace transform of x gives us this 1 over s plus 1 to the 4th power. And if we look on our sheet, our A sheet somewhere, we say, that looks suspiciously a lot like that, right? Because we have s to a power in the denominator. Okay, so we'll write that down for reference by the side. So we have the, so Laplace transform of e to the c t, t to the n is n factorial over s minus c to the n plus 1. So now we say, all right, we want to make this look like that. We want to make it fit the mold. So we say, okay, let's move up here. So this s plus 1 to the 4th, okay, so that's capital X. Well, we see here 4 needs to be n plus 1, so we have 3 plus 1. So we're going to write this as s minus 1 to the 3 plus 1. That means we want to have a 3 factorial upstairs, so we put a 3 factorial upstairs. Well, 3 factorial is the same as a 6, so 1 6, and 3 factorial cancel. So we've rewritten this so it matches this form. Because that's oftentimes what happens when you're doing inverse Laplace transforms. You're saying, fit the mold. What does it look like? And now we're saying, perfect, take the inverse Laplace transform, and what do we get? Well, so x, which is the inverse Laplace transform of capital X, is 1 6. And now we say, okay, c is minus 1, and t is 3. So it's e to the minus t cubed. And that's it. We're done. We did it. Woohoo! Now, what could we do? Well, we could check our answer, right? Because we could actually plug it into this differential equation. And if it satisfies the differential equation, life is good. Life is wonderful. But, well, we just trust that. Now, you might ask a question, do we need the 1 6? So the 1 6 came out of the process, but if you look at this differential equation, what do you notice about it? It is linear. And what do we know about linear differential equations? Well, it says we can do superposition. Now you might say, well, there's not a lot to superposition if you only have one solution. Well, there is something which says you can scale. So we can take this solution and we can scale it by any amount. So another answer could be just e to the minus t cubed. That's also perfectly valid. In fact, any multiple of e to the minus t cubed, except for 0, is the correct answer. So, wow, this is cool. Because we couldn't have done this problem before. There's just nothing for us to hold on to. We couldn't have done any variation parameters because we didn't have a solution, or we couldn't have, I guess variation parameters is for the non-homogeneous, but there's something called reduction of order. Okay, we couldn't have done that. We didn't have a solution, but we found one. Isn't that wonderful? I think it is. All right. Well, anyways, thanks for finishing up these 2 problems with me, and I hope it helps, and I hope you're having a good time. All right, we'll see you again.